Okay, just to recap, and I'm actually going to write these down here. So when you have side angle, or you have angle side angle, you want to use law of sines. Whenever you have side, or side angle side, you want to use law of cosines. And it doesn't matter what side you start off with, because we just did this twice, right?
Yeah.
Just don't forget the 2, I guess.
Yeah. All right. Yeah, I got, okay. So,
and make sure that the angle you're actually solving for is opposite the side that's actually the thing that's on the side on the equal side and by itself. That's the other thing.
Okay.
You see how you have beta here and you have b there? So that b squared goes on this side, and then the beta is the angle you're actually solving for.
Okay.
It's pretty straightforward.
Yeah, it makes sense now. When I do it, it's not too bad.
All right, what's next on our list? Oh, so here's another one of those questions. So in this question, what do you actually have? What did they give you for question number 4?
So let's see. They gave so they gave 2 sides and an angle.
Right.
So
which one of those laws are going to use then for that question?
The one we just did?
Yep.
Okay.
Because you have side, angle, side, right?
Both sides, yeah.
So I want to see why that angle is not 54 degrees. Are they just trying to mess with you with the 46 degree angle? Let me read it. Vicinity of the island. The rangefinder indicates that the island is 396 feet from the position, and the ship is using the compass. She finds that the ship's azimuth direction is measured in angle.
So why does it have the 306 degrees and then the 46?
I'm thinking that the angle between those two, because the compass is using how many degrees from due north, but the ship is to the west of due north, right? So the angle between the two actual lines should be 54 degrees. I think that the teacher's doing that to try to throw you off.
Oh, so you're just...
I'm taking the 306.
Yeah.
And I'm taking 360 minus 306 to find the angle between the two.
Oh, and for some reason they just gave you an angle of the north to the side of the island, right, for no reason.
Because the ship is using, I guess, is that azimuth? Is that what that word is there? Direction measured from the angle from the north. So the island, and that island is 46 degrees from north. The island is 46 degrees from true north, but the ship is past true north.
Right.
Let me see if I can blow this up so I can actually look at that picture. So, okay, so it's saying that the angle that you want to use is 54 degrees.
Okay.
It's saying that the island is 46 degrees from true north, and that the ship is 306 degrees from true north.
Okay.
So if I add 46, okay, so let me draw a picture of this to show you what's going on, and so I can wrap my brain around it so we use the right angle. So I have my ship here, and then I got my island here, and there's true north. And from there to there is 46. And from here to this line is 306. So how many degrees would take me back to true north? So
it would be would it be 54 minus 46?
It would be 54 plus 46. Do you see how I'm drawing that?
Oh, okay.
So that the angle between, from her location, if I draw another picture, so the angle between that guy and the boat and the island would be those two numbers added to one another.
Okay.
Because here's your true north, right? And I know in order to get back to true north, this is 54 degrees, right?
Yeah.
And in order to get to the island, I have to add another 46 to it.
Okay.
So that makes it a total of 100 degrees.
Oh, okay.
Does that make sense?
Yeah. Interesting.
It's a stupid way of asking a question, but whatever.
I got it. So basically, it's kind of tricky because they give you like half of the angle, and you got to figure out the other half, basically.
Right.
Okay.
Because you have to measure it from true north, right?
Yeah.
So, how big are our sides of our triangle? Because I don't have those numbers in front of me. How far into the boat?
So, one side is 587, and the other side is 396.
And I want to find that side.
Right.
So I'm going to clean this picture up.
It's a pretty good picture.
Thanks.
Okay, so
and that's one. Ooh, I hate when I do that. This is 100 degrees.
So I put the angle we do know. I put it as B, and it's 100.
Okay.
And then we're looking for little b.
Okay. So tell me the equation that I'm going to put together here. Stick the numbers in.
Okay. So let's see. 396, 587. Okay, so this one's, is it a little different because we have, oh wait, no, never mind. Okay, so we got 100 squared equals.
Okay, I'm going to stop you there. The little b, is that a side or an angle?
Oh wait, no, you're right. Oh wait, so does that mean that 100 squared goes on the other side of cosine at the end?
Yeah, it's not even squared. It just goes in with the cosine.
Right, okay, right,
This
okay.
one is kind of just straightforward, right? We're
Yeah.
solving for this thing right here, right?
Yes.
So all we got to do is just literally just stick in the numbers and we'll get the answer. So tell me what numbers to write, just so I know you put them in the right spot.
Okay, so we got, so you got b squared equals 396 squared plus 587 squared. I'm writing it down.
That's fine.
396. And then it's minus 2. And then I have 396 in parentheses, and then times 587.
Keep on going. Last little part.
And then cosine, and then 100.
Right.
All right. So 396 squared. That's a big number.
Well, these numbers are gonna be huge.
All right, so I got 156 816 plus 587. 344 569. Which is 501 385. Minus, okay, so we get
582114. 582114. 7. And then I'm going to take the square root of the whole thing. Okay. Does it say where we're supposed to round for this?
It just says round to the nearest foot.
Okay.
So, John.
Yep.
Do you just type the whole thing in the calculator? Like,
I type it in exactly how it's written because I have a TI 84. Do you have like a scientific calculator like that?
Yeah. So you did 396 squared plus 587 squared
minus 2 times 396. You know, just exactly that as it's written. And I don't even put any. I don't put a multiplication symbol between the number and the cosine. I just write the number, then put cosine 100.
Okay.
And then at the end, I got that big number, and then I just took the square root of that number in order to find b.
Okay. Oh, yeah, okay. I gotcha. Okay, I got the same thing.
Good. Sweet.
Yeah, I guess that was easier. So maybe that's why he made it tricky.
Right, because he had to put some kind of level of difficulty in it, right?
Yeah.
And I wonder how many folks he's gonna trick with just using the 46.
Right.
It's almost not fair when you're a teacher, because I used to do that kind of stuff to my students. I'm not gonna lie.
Okay, that was cool. That works.
All right, let's see what's next.
Man, it's been a while since I've seen one of those imaginary eyes.
This is actually not that hard.
Okay. I remember, I think, like, wasn't it I is equal to -1?
I'll go through that with you. It's a you actually don't even need it for this stuff though.
Oh, okay.
Because they're writing stuff in what's called polar coordinates.
Okay.
So you can go from a complex number to trig using polar coordinates. I'm going to start it this way. Let's say that I want to map an imaginary number. All right. So this is the real axis, and this is the imaginary axis.
Oh, right. I read over that real quick.
So anything with an I attached to it, that's going to go on this axis, and anything with just a regular number is going to go on this axis. So you can plot a point. So I think the thing was, I forgot the number now. So we have 2 plus 2 root 3i. So this is the y part, and that's the x part.
Okay.
So if I want to plot what's called r, I just plot those coordinates. So here's another way of writing it. It would be like 2 comma 2 root 3. Because that's in terms of Cartesian coordinates, or just regular, like, graphing.
Okay.
And another thing you have to remember is this is the cosine part, and that's the sine part. Right?
Right.
And that's like straight up from our unit circle stuff, right?
Yeah.
So I'll just plot this. I'll say this is 1, 2. And then root 3, I guess, is like 1.1, something like that. So 2 times 1.1 is like 2.6. Let's call it 3, just for giggles. So the number would be there. And then the distance that it takes to go from there to there, they call that distance r.
Okay.
Well, any line that I draw from the origin can be written as a right triangle, right? So I have this as being 2, and this as being the square root of 3. I'm sorry, 2 times the square root of 3. Let me rewrite that a little better. And right here is my theta. So in order to find out what r is, they use this thing called the modulus. Have you heard that word before?
It does not sound familiar.
Okay. Let's say that this is some number a, right? So to find r, these two lines mean magnitude. So how big it is.
Okay.
And you would just put your complex number inside of here. Okay. Here's how you figure that out. You use the distance formula, just like you would in algebra class. So the distance formula says that it's the square root of x squared plus y squared. You ignore the imaginary number. And I guess I should write this the same way so I don't confuse you. So this is 2 root 3 I. And so I'm gonna ignore the I.
Okay.
So what is x equal to? It's right there.
So that's the 2 root 3?
No, the x is just the 2 part. You see how I have x and cosine written right there?
Oh, yeah, sorry, backwards. Yeah, 2.
So I'm just going to square that.
Okay.
And then what's your y equal to?
The 2 root 3?
Uh-huh. So I'm going to put that in parentheses, 2 square root of 3, and I'm going to square that. You notice that I did not put the I with that, right?
Yes.
And so I just do that math. So r is going to be equal to the square root of 4 plus 12. Do you need me to show you why that's equal to 12, or do you get that? I'll break it down. I'll break it down just in case.
I put it in my calculator and I got it, but I forget manually with the radicals. It's been a while.
Okay. So that power of 2 goes to both of those numbers. So this is 2 squared times the square root of 3 squared.
Okay.
2 squared is what?
4.
And the square root of 3 squared is what?
6.
Well, this square root right here, or that power right there, and this square root, they kind of cancel each other out. So that's just equal to 3.
Oh, okay. That looks familiar.
And so then 4 times 3 is 12, right?
Okay.
So r is equal to the square root of 16, and that's equal to 4. And you'll notice that that is just straight up Pythagorean theorem, because what kind of triangle did I draw there?
Just a right triangle?
Just a right triangle. It's a regular old right triangle. So if that's the case, and that's a regular old right triangle, so I'll redraw it big here. This is theta, and that's 2 root 3, and this is 2. How do I solve for theta? And this is something that we worked on kind of the past 2 times we met with each other. What sides of the triangle do I have?
The 2 legs. So we have A and B?
You have A. SOHCAHTOA is what I'm trying to get you to use.
Oh, and I'm sorry. And which one were we solving for?
We're solving for theta. I want to know what theta is, where it is. You see where it is in my right triangle?
So it's the left angle?
It's the left angle, yes.
Okay, so that's oh man, so this is just what we were doing.
I don't want you to make it any more complicated than it is. These are the 3 letters I'm looking for. I'm looking for either the hypotenuse, the opposite side, or the adjacent side. This is just regular old, like, simple, basic trig. It's not the hard stuff.
Okay, so for that, since we have the opposite and the adjacent, we could use tangent?
Right.
Okay.
So the tangent inverse, because I'm looking for an angle, right?
Right.
Is going to be what over what?
So it's, I see what you're saying. We're looking for angle. I forgot about that. Okay. So we're looking for sine over cosine?
Right. Oh, which you could actually get straight out from your complex number, right? So what's the sine side? What number represents the sine side?
The 2 root 3.
Uh-huh. And what represents the cosine side?
And then it's 2.
What happens to the two 2's?
They cancel out.
And what is the inverse tangent of the square root of 3? You should actually know this.
Oh, jeez.
Because that's something we worked on yesterday, too. Sorry, man. I'm going to make you work.
Oh, right. So that's... the inverse. So that's 60 degrees?
Yes!
All right.
Yes, that's 60 degrees.
So, John, the only part I'm confused on, when we were working for solving R, and then, so ultimately R equals 4, right?
Right.
And then I was writing down, and then you went on to drawing the triangle that we just solved for the theta.
Uh-huh.
But I missed the point on why we were doing that last part down there.
Okay. Look at the way that your worksheet is lettered or is answered. You see the fill in the blanks there?
Yeah.
So any complex number, let me see here. I need to erase some of this. And I'm going to give it to you in general first, okay?
Okay.
So any complex number a plus bi can be written in terms of polar coordinates as r times the cosine of theta plus sine theta I. So in our example, we've got 2 plus 2 square root of 3 I, right?
Right.
And now I need to fill in all the blanks. So what is our R?
Oh, okay. So R is 4.
And then the cosine of what? What's our theta?
The cosine is 2.
No. What did we just solve for? How many degrees is our theta? That's what I'm asking you for.
Oh, it's 60.
Yeah. So I can put cosine of 60 degrees here plus the sine of what?
So is that also 60?
That's also 60. It's the same theta. The only difference between that theta and this theta is that one of them's imaginary.
Okay.
So that's actually how you fill in the blanks for that. That's why we solve for all that stuff.
Oh, okay. Okay.
Do we need to do another one just to make sure you got it, or do you have it now? Did you get the piece that you needed?
Yeah, I think I got the piece I needed. It's just I'm drawing down the way you drew the triangle. I'm just making a note and referencing why you did that, just for a visual.
Just remember that any complex number can be written as a right triangle. The real part is the x part. The imaginary part is the y part. And because you can draw a right triangle, you can always find the angle theta from the origin.
Oh, we may have broke up, John. I saw my internet go out, and then now it's in.
Okay. Did you hear what I said there? Sorry.
It's like a movie. You were going to say, like, the most important part is, and then it broke up.
I'm sorry, man. It's like the best scene. Okay. Okay, I'll repeat it.
All right.
The most important part that you need to remember is that any complex number can be written as a right triangle. The real part is the cosine part, or the x part, and the imaginary part is always going to be the y, or the sine part. So then you can plot those two parts of that number, draw a right triangle, and then figure out how many degrees it is from the origin.
Oh, okay.
And whenever you see these absolute value marks, and it's going to be important when you do vectors, just realize that you're just using this equation, that x squared plus y squared, because it's asking you for the magnitude of that vector.
Okay.
That just means how big is it. That's why we didn't have any theta or anything with that. We just used that to figure out how big r is.
Okay.
And then you just fill in the blanks, because you got your r, now you can, once you find your r and your theta, you just fill it in, and then you have the answer.
And when we've to figure theta, and we had the opposite and the adjacent, so we used tangent. And then after that, how did you know to use the inverse of tangent?
Because what are we solving for? What does theta represent inside of the triangle? What is theta?
I forget. Like,
is it a side or is it an angle?
Oh, it's an angle.
And whenever you're solving for an angle, what kind of trig functions do you use?
Okay, the inverse?
The inverse. That's what we worked on the past 2 days, right?
Right, okay.
Remember, when you're solving for a side, they have to give you an angle, and then you can just put in the numbers and then get the side. When you're solving for an angle, you always have to use an inverse function, because that's the difference between the two.
Okay. Yeah, that helps. We need...
Let me show you a little something, okay?
Okay.
So let's say we wanted to work this question backwards, right? So I'm underneath this part right here, just so you can see where I am. You see where I underlined?
Yeah.
Okay, so I'm going to work this backwards to see if I get that imaginary number back. So
okay.
I'm going to take 4 times, what is the cosine of 60?
What is it?
What is the cosine of 60 on your unit circle?
Yeah, 1/2.
Uh-huh. Plus, what is the sine of 60?
√3/2.
And then I have that I there, right?
Yeah.
Distribute the 4 through that. So what's 4 times 1/2?
2.
What is 4 times √3/2?
Let me see. I don't know.
Okay. Let me make some space so I can help you through that, because I want you to see this. I want you to see why all this stuff works out.
Okay.
So I'm going to write these numbers separately. 4 times √3i/2. What happens to this 2 and that 4?
They cancel out?
They cancel out. This 2 goes away, it becomes a 1. And then what happens to this 4?
It cuts in half?
Yep. It becomes a 2. So you get 2 √3i. Isn't that the complex number we started off with in the first place?
Oh, yeah. Okay. So that's a way to check it.
That's a way to check it. But when you're writing stuff in terms of, they call it polar coordinates, you just leave it just like this. Because if you do the extra steps that I did, you just get the number back. Which makes no sense, right? Why even bother doing that?
Right. Okay. And what did you call that again? You said it's the polar coordinates?
It's called polar coordinates.
Okay.
I think your teacher is calling it the trig representation of a complex number, but the math people call them polar coordinates.
Okay.
And in physics, we use that all of the time because there are a lot of questions that you can't solve in the real world. So you switch it over to the complex world because it simplifies a bunch of stuff, and then you switch it back. So we use them all the time.
Oh, okay.
Not that you will ever use that in your real life, but if you're an engineer, you would use it. You know what I'm saying?
You would?
Yeah. If you're a financial manager person and you're trying to do like different models of things that are actually going on in the real world, you would use them too.
Oh, okay.
That's why most of the hedge fund managers are ex-engineers. It's crazy.
Yeah.
Because there was way more money in finance than there is in engineering.
Yeah.
I think I picked the wrong profession, but I don't. I love what I do. I don't know if I would want to crunch numbers all day long. So.
What did you go? Did you say you went to school for physics?
Yeah, I went to school for physics. But a lot of my friends that went to school and graduated with me, especially from UVA, they end up becoming analysts for big banks.
Oh, really?
And they moved to New York, and they're making six-figure salaries now.
Were they also physics majors?
Yes, they were.
I see.
I couldn't do it.
Okay. Man, I remember the complex numbers and all the different types of rationalizing the different numbers as well. And I know we ran into a lot of those, and it's like some are coming back to me, and I forgot some of those.
Right. Well, if there's anything that you need to refresh your memory on that you want to work on, just let me know, and then I'll help you.
Okay. All right. Well, this was a good start to this. I'll just keep on going tomorrow, and I'll see where I go. And then I think we meet up on Tuesday again.
Yeah, we made up on Tuesday again. I think like for the next 3 or 4 questions, you're going to be using this stuff.
Okay.
And then there's something called, the dude's name starts with a D, where you're actually like taking the 5th power of a complex number. So just follow the formula. So you're going to do everything that I just did, except for the formula looks like this. Like let's say I have this one. To the 5th power, right? All I have to do is take my R value and raise it to the 5th power. So I would calculate whatever R is.
Yeah.
And this is the last thing I want to do with you. Then I would do cosine of 5 times, and you're going to actually have to do this in, well, it might work in degrees. So you do 5 times 60 plus the sine of 5 times 60 and then I. So whatever this power is, your front number gets raised to the same power, and then you multiply that power inside of the trig function. That's all you do.
Oh, I see.
And then once you do that and get the answer, that's your answer. You would actually solve it all the way out like we did here.
Oh, okay.
And you might actually have to change this to pi over 3 in order to get it to work out. It might have to be in radians. I can't remember if it works for degrees too, but I know it works for radians.
Okay.
I think you're actually going to have to do that. Is 5 pi over 3, that's not 300 degrees, right? No.
Yeah.
Is that 300 degrees?
Yeah.
Okay, then it will work out. It'll work out either way.
Oh, okay. Oh, I see what you're saying.
Because if it's pi over 3, then it's 5 times pi over 3, which is 5 pi over 3. And I guess that is 300 degrees, so it'll still work, even if you have it in degrees.
Okay. Interesting.
So just follow the formula. I guess that formula should be in your book or in your notes or something, whatever sort resource you're using.
Okay. I think I saw it when you were talking earlier. Yeah.
His name starts with a D. I just can't. I'm having a brain fart right now. I can't remember what his name is. Devardiers or something like that. It might. I don't know. I might be making that up.
Oh, I think I found it. D. Movers?
D. Morvers, yeah. Yeah.
Powers of, yeah, actually, that's next. Here it comes.
So you should be able to get through most of that, and then we can discuss what you couldn't do on Tuesday.
Okay. Yep. Sounds good to me.
All right. I'll see you at about, I guess, 8 o'clock your time, 8 or 8:30 your time on Tuesday.
Okay.
As soon as I'm open, as soon as the kids go to sleep, I will give you a text and let you know, and then get online.
All right. That sounds good.
All right, man. Well, have a good couple of days.
All right. You too. Thanks, John.
All right. No problem.
All right. Bye.
Bye.